Hello everyone, welcome to my video. Thanks for taking your time to watching it. I'm going to tell you something about percolation in weight-dependent random connection models, and it's built on joint work with Peter Gratzer and Peter Merters. First, maybe to percolation. So consider a random graph G with infinite vertex set, countable infinite vertex set, but each vertex only has finite degrees. And we say this graph percolates if it contains an infinite connected component. And we are actually considering random graph G, which have involved a temperature parameter beta, which controls the edge density on the classic way. Increasing the temperature means more activity, means more edges on average. And we are asking ourselves, okay, if this graph percolates, but then we reduce the temperature, does this destroy the infinite connected component? In other words, we say there is a percolation phase transition if there exists a critical temperature beta c, strictly between 0 and infinity, such that the graph does not contain an infinite connected component if the temperature is below that threshold, but it does if it's above. And are there actually graphs with beta c equals to 0, so that there's no subcritical phase where the graph does not percolate, because that would mean this graph is very robust, because reducing the temperature can never destroy the connectivity within the model as long as there's a minimum of activity is going. Here we focus on graphs with long-range dependencies and heavy-tailed degree distributions. And next, I am going to describe to you the model, and later I give some examples and our main result. So our graph G beta lives on a Poisson point process of unit intensity on RD times 0, 1. We focus on D larger than 2 here. The one-dimensional case is actually covered by Peter Gratzer in another video. And you can also think of, we have vertices X that are embedded in the RD, and each vertex is given an independent and uniform distributed mark. And given positions and marks, we connect each pair of vertices independently by an edge with this probability, which depends, okay, on the temperature beta, then somehow on the marks and on the distance of the spatial distance of the vertices. So here, rho, the outer function, is an integrable, non-increasing profile function. It goes to 0, 1 because it's a probability, and it's non-increasing. So assume temperature and marks are fixed, but then I increase the distance, then I decrease the probability of being connected. So we prefer actually short edges here. And the G, which contains the marks, is a symmetric and non-decreasing function we call kernel function, and it models how the influence of the marks to the connection mechanism. And here non-decreasing means if I fix the distance, but I want to increase the probability of being connected, I have to actually decrease the marks. So I have to send the marks of the vertices to 0. And we have the temperature beta here. Okay, I already described what this is doing. And without laws of generality, we actually assume that this rho of norm of x to the d integrates to 1. Because if we do so, the degree distribution only depends on the kernel G. So the degree distribution in the graph is only modeled by the influence of the vertices marks. Okay, and in this model there are contained some well-known models, and we can derive them from our setting. I give you 2 examples. The first one already opened here. It's the long-range percolation model. In this model, there are actually traditionally no vertices marks. So the kernel function is just a plain kernel, which is always equivalent to 1. So the marks does not play any role. And I connect 2 vertices independently just depending on their distance with this function rho here. And Newman and Schulman showed that in this case, there exists a critical or percolation phase transition. That means the beta C larger than 0. And if you do not want to consider this specific function rho, you can actually extend the result to arbitrarily function rho that decay polynomial, and this was done by Penrose in 91. Another very interesting model is the so-called Boolean model. In this model, traditionally, we have our points in the space, and we assign to each point a heavy-tailed distributed radius. And two vertices are connected if their corresponding radii intersect, or the balls, not the radii, if the balls I draw around them with the corresponding radii, if those balls intersect. And here we derive the heavy-tailed radii as a negative power in terms of gamma of the vertices marks, and we take the sum of them, and as a profile function, we take an indicator function. So if we go back here, what does this mean? So we have the distance of the vertices here to the power of d divided by the sum of radii, also to the d. So, and this all put in an indicator function. This basically means we connect both vertices when the ratio of distance and radii is below some threshold, a. And this actually leads to a heavy-tailed degree distribution with power law tau given by 1 plus 1 over gamma. And we could also consider another Boolean model, which is given by the min kernel G min. Here, the difference is not the balls must intersect, but the vertex with a smaller ball must be contained in the larger ball. And Gouret showed for this Boolean model that there exists a percolation phase transition. So far, neither the long-range edges from the long-range percolation model nor the heavy-tailed degree distribution from the Boolean model alone could remove the subcritical phase and ensure beta C equals 0. What happens if we combine both effects? This leads us here. So we take the polynomial decaying function rho from the long-range percolation, but G sum or G min, the kernel function from the Boolean model. This is what we refer to as soft Boolean model. So before, in the Boolean model, we connected two vertices if their corresponding, if the ratio of their distance divided by the sum of their radii were below threshold A. Yeah, if yes, we connected, if no, we didn't. And here we connect the two vertices if this ratio is below some heavy-tailed random variable. Another model we could consider is the same rho, but different kernel. It's what we call the preferential attachment kernel. This here leads to the age-dependent random connection model. This model occurs as a weak local limit of a preferential attachment type growing sequence of graphs. I will not go into account. So if we take one of these two models, then Peter Gratzer, Peter Mertens, and me have shown that we can indeed have a parameter regime where beta C equals 0, namely if gamma is larger than delta divided by delta plus 1. But if it's not, the beta C is larger than 0. So why is this happening? Shortly, two words, it's if you want to build an infinite path, you need a strategy to go from a powerful high degree vertex to an even more powerful degree vertex. But we are embedded in space, so these very powerful high degree vertices are typically far apart. So to reach them, I need to use connectors. And we have shown that this strategy of using a normal vertex as a connector to connect a powerful vertex, connector very powerful vertex, is only working if sufficiently large power law meets sufficiently large long-range effects. So yeah, I'm out of time. So this is what I wanted to tell you. Thank you for taking your time. I'm looking forward to meet you all in Mannheim, not personally, but kind of in our Zoom conferences. Have a good day. Bye.